Hello students, my name is Mr. Abiyantana. Welcome to grade 11 Mathematics Unit 2, which is a graph of rational functions. So under a graph of rational function, we'll try to cover these ideas. One, a vertical asymptote. How we'll determine vertical asymptote of a rational function, and also horizontal asymptote or oblique asymptote. We'll try to see the conditions when a graph of a rational function will have a horizontal asymptote and oblique asymptotes. And similarly, we'll try to draw graphs of a rational function, and some basic properties will be stated here. So what is a vertical asymptote of a rational function? You know that a rational function is a function which is a quotient of two polynomials of p and q, where q is different from 0. So vertical asymptote of a rational function f of x equals to p of x over q of x is x equals to a, such that q of a equals to 0 and p of a must be different from 0. Meaning to be x equals to a is a vertical asymptote of a rational function. P of x must be different from 0 and q of x must be necessarily equal to 0. So if it satisfies this condition, the line x equals to a is what we call a vertical asymptote, or x equals to a is a vertical asymptote. As x tends to a, then the function f of x will closer to either a positive infinity or to a negative infinity. What if q of a equals to 0 and also p of a equals to 0? Meaning if a makes both the numerator and denominator equals to 0, then the graph will have a hole at x equals to 0, or it may be a vertical asymptote. So if x equals to a makes both p of x and q of x equals to 0, it needs further study, meaning it will have a hole or it may have a vertical asymptote. Now let's see when a graph of a rational function will have a horizontal asymptote, oblique asymptote. So there are conditions. Now let's see how to determine a horizontal asymptote of a graph of a rational function. If the function f of x is defined by this as a form of a quotient of two polynomial p of x to q of x, where this is a polynomial function of degree n and this is a polynomial function of degree m. So there are conditions to determine a horizontal asymptote. So the first case, y equals to 0 is a horizontal asymptote if n is less than m, implies when degree of p of x is less than degree of q of x. So n and m represents degree of p of x and q of x respectively. So when degree of q of x is greater than degree of p of x, necessarily y equals to 0 is a horizontal asymptote. Then the second case, if both p of x and q of x have the same degree, let n equals to m if they have the same degree. So the horizontal asymptote is a coefficient of p of x over the leading coefficient of q of x, that is bm. Implies the horizontal asymptote of the graph is the quotient of the leading coefficients of p of x to q of x. Then the third case, the graph will have an oblique asymptote. So when it will have oblique asymptote, if n equals to m plus 1, which states if degree of p of x is greater than degree of q of x by 1, then this rational function will have an oblique asymptote. And how we can determine its oblique asymptote? The oblique asymptote is a quotient of p of x to q of x. You know how to determine a quotient of a rational function? We'll divide p of x by q of x. So the quotient is an oblique asymptote. Example 1, what are the vertical and horizontal asymptotes of this function? F of x equals to x minus 1 into x plus 1 over x plus 2 the whole square, then times x plus 1. So to be vertical asymptote of this rational function, a number x must make only the denominator equals to 0. So what are numbers that makes the denominator equals to 0? Here, what number will make this 0 at x equals to minus 2? So let's check x equals to minus 2 is a vertical asymptote or not. So here, it makes the denominator equals to 0, and at the same time, we have to check that the numerator must be different from 0. So if we substitute minus 2 on the numerator, is necessarily different from 0. So x equals to minus 2 is a vertical asymptote. And the other number that makes the denominator 0 is x equals to minus 1. So it makes the denominator equals to 0, and it must make the numerator different from 0 to be it is a vertical asymptote. But if we substitute here minus 1 plus 1 is 0, that makes the denominator 0, and minus 1 plus 1 is also equals to 0. So x equals to minus 1 makes both the denominator and the numerator equals to 0. So when a number x equals to a makes both the denominator and numerator equals to 0, it needs either further simplification or it may have a whole at that point. So x plus 1 is common factor for numerator and denominator, so we can cancel. So the resulting function will be x minus 1 over x plus 2 the whole square. Now we can check it again. Now, is x equals to minus 1 a vertical asymptote for the new Lie function? It's not. Because when we substitute x equals to minus 1 in place of x, it does not make the denominator equals to 0. So at x equals to minus 1, the graph will have a hole. It will have a hole. So how we can determine the hole on the graph of this rational function? To find or to determine a hole of rational function at x equals to minus 1, substitute minus 1 on the simplified function. So at x equals to minus 1, we have to substitute minus 1 on the simplified one. So the value of y is f of minus 1. That is, f of minus 1 equals to minus 1, then minus 1 over minus 1 plus 2 the whole square. Now minus 1 is minus 2 over minus 1 plus 2 is 1 the whole square. That's 1. So this is equal to minus 2. Therefore, the hole on the graph of this rational function is a point minus 1 comma minus 2. Rational functions and their graphs. To sketch a graph of a rational function, we have to determine or we have to follow these procedures. First, determine x-intercept and y-intercept of a graph if it exists. 2, determine vertical asymptote. It may have more than one, or a hole if it exists. And also determine horizontal or oblique asymptote of a given rational function. Then let's draw a graph of this rational function. F of x equals to 5x plus 2 over x minus 1 then into x plus 2. So to draw graph of this rational function, let's determine vertical asymptotes. The vertical asymptote is a number x that makes the denominator equals to 0. So if we substitute x equals to 1 here, 1 minus 1 is equal to 0. So x equals to 1 is 1 of a vertical asymptote, and the other one, x plus 2. At what number this will be 0? At minus 2. Then the other vertical asymptote is x equals to minus 2. Now let's draw these vertical asymptotes on this coordinate plane. Why we will use this broken line? Because the graph of a rational function will never touch and cross this vertical asymptote. A graph of a rational function will never cross or touch these vertical asymptotes. There is a possibility of a rational function to cross either horizontal asymptote or oblique asymptote, but a graph of a rational function will never touch and cross a vertical asymptotes. So these are a vertical asymptotes, and what is a horizontal asymptote? To determine a horizontal asymptote, check degree of numerator and denominator. A degree of a numerator is 1 because it's linear. Here, the denominator is product of two linear factors, so degree of the denominator is 2. Therefore, when degree of the denominator is greater than degree of a numerator, a horizontal asymptote is y equals to 0. So the horizontal asymptote is the horizontal line y equals to 0. Now to draw a graph of this rational function, we need to determine also x-intercept. X-intercept at 5x plus 2 over x minus 1 then times x plus 2 equals to 0. So if we solve this, 5x plus 2 equals to 0, because when we make it crisscross, this will be 0. So x equals to minus 2 over 5. Let's try to locate this point. Minus 2 over 5 is approximately negative 0.4. So the graph will intersect the x-axis at this point. And what is y-intercept of the function? The y-intercept is at x equals to 0. So what will happen if we substitute x equals to 0? So f of 0, that is a y-intercept, equals to 5 times 0 plus 2, that is 2, over 0 minus 1 is minus 1, then into 0 plus 2 is 2. So the value of this, that's 2 over minus 2, it's equals to minus 1. At x equals to 0, the graph crosses at y equals to minus 1. Now, let's draw a graph of a rational function. To draw a graph of a rational function, you can start either from the left or from the right side. This is x equals to minus 2, that's a vertical asymptote. This is x equals to 1, that is a vertical asymptote. As x closer to minus 2 from the left, what will happen the graph? Is that closer to positive infinity or closer to minus infinity? So to identify this, substitute some number x which is closer to minus 2 from the left. Let x equals to minus 2.01. And it is advised to take a very closer number to the vertical asymptote. Here our objective is not to evaluate the value at x equals to minus 2.01. Our objective is to determine only the sign. So if we substitute here minus 2.01 in place of x, it will be negative 10.02, then plus 2. Then at x equals to this, the numerator have a negative sign. Then over at x equals to minus 2.01, this is also negative. So put a negative, because here the objective is not to evaluate, it's to determine the sign. Minus 2.01 plus 2, it's also negative. So what is the quotient of this? The sign of the quotient? Negative over negative, negative. So the quotient will be negative, which implies as x tends to minus 2 from the left, f of x will closer to minus infinity. So the end graph will point downward. We'll put here. So as we go upward, the graph will look like this. In the same way, if we substitute a number x which is closer to minus 2 from the right, let x equals to minus 1.9. Therefore, let's evaluate what will be the sign here. Minus 1.9 times 5 plus 2, it's negative. You can check the sign. Then over minus 1.9 minus 1, this is also negative. Then minus 1.9 plus 2, this is positive. So negative over negative is positive. So the function f of x will closer to positive infinity. So we'll put the arrow to this side. So as we go down, and we know that it will intersect the x-axis at this point and the y-axis, so it will go to this direction. In similar way, as x closer to 1 from the right, as x closer to 1 from the right, we can check whether the function f of x will closer to a positive infinity or minus infinity. So when x is closer to 1 from the right, substitute some constant number which is closer to 1 from the right. Let's consider 1.01. It's advised to take a number which is more closer to a vertical line. And our objective is to check only the sign of the quotient, not a magnitude. So at 1.01, 5 times 1.01 plus 2 is positive, and 1.01 minus 1 is positive, and also 1.01 plus 2 is positive. So positive over positive is positive. That implies the function will closer to positive infinity. So the end graph of this rational function will goes to upward as x closer to 1 from the right. So put the end of a graph here. So put the end of a graph here, then it will go to this direction. Because it will not cross the horizontal asymptote, already we know. The graph intersects at this point. Then the other example, sketch a graph of a rational function. F of x equals to x cubed over x plus 1 into x minus 1. In the same way, let's determine first a vertical asymptote, horizontal asymptote, oblique asymptote if it exists. Now, it's clear that x equals to minus 1 and x equals to 1 are a vertical asymptotes because at x equals to minus 1, the denominator is equal to 0. And similarly, at x equals to 1, the denominator is only equal to 0. So, let's denote x equals to 1 and x equals to minus 1 are vertical asymptotes. Vertical asymptote. And also, f of x equals to x cubed over x plus 1 times x minus 1. Degree of the numerator is 3. Degree of the denominator is product of two linears, which is 2. So degree of the denominator is greater than degree of the denominator by 1. So this rational function will have an oblique asymptote. How we can determine an oblique asymptote? It's a quotient which is obtained by dividing numerator to a denominator. So let's divide x cubed divided by the product of x plus 1 times x minus 1 is it's x squared minus 1. Now we can divide this simply. X cubed divided by x squared, that is x. X times x squared that's x cubed, x minus 1, that's x. Now if we subtract, x cubed minus x cubed is 0. So minus of minus x, it is x. Now this is the remainder because the degree of this is 1, which is less than degree of the divisor. Therefore, an oblique asymptote is a question that is y equals to x. This is the equation. Now let's draw this. Y equals to x is a straight line that passes through the origin. This is y equals to x. That is an oblique asymptote. The other vertical asymptote is y equals to. The other vertical asymptote, x equals to 1. And another vertical asymptote, x equals to minus 1. X equals to minus 1. When we draw the vertical asymptote, always we'll use a broken line because a broken line states a graph of a rational function will never cross and touch these lines, but the graph may intersect an oblique or a horizontal asymptote. So to draw, we can determine some points additionally. X-intercept or y-intercept. Then to determine x-intercept, let's solve this. X cubed over a product of this is already equal to x squared minus 1 equals to 0. If we recross this, x cubed equals to 0. So x equals to 0. So at the origin, the graph will intersect the x-axis. And what is the vertical asymptote? It is the same because the graph crosses the x-axis at x equals to 0 and it intersects the y-axis also at that point. Then, to draw a graph of this function, as x closer to 1 from the right, what will be a graph of or a functional value of f of x? So is f of x closer to a positive infinity or negative infinity? So we'll take some constant to the right of 1. Let's take x equals to 1.01. If we take 1.01, 1.01 the whole cube, it's positive. 1.01 plus 1, it's positive. 1.01 minus 1, it's positive. So the quotient of these numbers is positive, implies the functional value will closer to positive infinity, which implies as we closer and closer from the right to this vertical line, the graph will go vertically upward. So to draw the graph, as x closer to 1 from the right, f of x is closer to positive infinity. So it will go to this direction and will go to this side because only we have this point that the graph will cross the oblique asymptote. And similarly, as x closer to 1 from the left, as x closer to 1 from the left, let's take 0.9. 0.9 the whole cube, it's positive. 0.9 plus 1, it's positive. 0.9 minus 1, it's negative. So positive over negative is negative, which implies the graph goes downward as x closer to 1 from the left. So it goes this direction and it crosses the x-axis and the y-axis at the origin. And as x closer to minus 1 from the right, as x closer to minus 1 from the right, what looks like a graph of this rational function. So we can take also some constant which is closer to minus 1. Let's take negative 0.9. Negative 0.9 the whole cube. A cube of negative number is negative. Negative 0.9 plus 1 is positive. Negative 0.9 minus 1, that's negative. So this is negative, this positive, this negative. So the quotient will have a positive sign, which implies the graph of the function will closer to positive infinity when it is closer to minus 1 from the right. So we'll connect like this. And also, what if when x is closer to minus 1 from the left side? Let x closer to minus 1 from the left. Then f of x will closer to either positive infinity or minus infinity. So we can take some constant number which is closer to this. Let's take negative 1.1. Negative 1.1 the whole cube, that's negative. Negative 1.1, this negative. Negative 1.1 minus 1, it's negative. So negative over, both these are negative, so it will be positive. So negative over positive is negative. That implies f of x will closer to minus infinity. Graphically, it implies the graph will fall down as we closer to minus 1 from the left. So we'll move like this and it will bend through the oblique asymptote. So this is a graph of this rational function. Then another example, which of the following function could most likely be drawn in the figure below? So if we observe this graph, there are two vertical asymptotes and there is a horizontal asymptote which is red color. There is no oblique asymptote. So what could be equation of a rational function that can represent this graph? Now from this we have this information. X equals to minus 4 is one of a vertical asymptote. Then the other one, x equals to minus 1 because it passes through at x equals to minus 1. These are the two vertical asymptotes. And what is another information given here? The horizontal asymptote, that is y equals to 0. So y equals to 0 is a horizontal asymptote. This information tells us degree of the denominator is greater than degree of the numerator. And there are another information. At x equals to 0, the value of y is 1. That is 0, 1 is y-intercept. And there is no x-intercept of this graph. So from the choice below, we'll identify which function could represent this graph. Now, for the above graph, from this choice, we'll try to identify which one will represent the graph. Here, x equals to minus 1 and x equals to minus 4. X equals to minus 1 and x equals to minus 4 are vertical asymptotes. And also, the horizontal asymptote is y equals to 0 because degree 1, degree 2. And what is a y-intercept at x equals to 0? 1 over 1 then times 4. So it's 1 over 4. Good. In the same way, let's do for b. Similarly, x equals to minus 1 and x equals to minus 4 are vertical asymptotes. X equals to minus 1, x equals to minus 4, and the horizontal asymptote is y equals to 0. Because still, this is constant, this is degree 2, meaning its degree is greater than degree of a numerator. And at x equals to 0, what is the value of y? That's a y-intercept. So 0 plus 1, 1 times 0 plus 4, that's 4. So 4 over 4, it is 1. So x equals to minus 1, x equals to minus 4, y equals to 0, and 0, 1 is y-intercept. Okay, similarly for this, x equals to minus 1, x equals to minus 4, and y equals to 0, horizontal asymptote. And at x 0, the value of y is also 0. 2 times 0, that's 0 over 1 times 4. Then finally for this, x equals to minus 1 and x equals to 1 are vertical asymptotes. The horizontal asymptote is y equals to 0. And at x equals to 0, what is the value of y? That's y-intercept of this graph. Minus 1 over 0 plus 1, that's 1. 0 minus 1, that's minus 1. So minus 1 over minus 1, it's minus 1. So here x equals to minus 1, x equals to 1, y equals to 0 is a horizontal asymptote. At x equals to 0, minus 1 over 0 plus 1, that's 1. 0 minus 1, that's minus 1. So minus 1 over minus 1 is a positive 1. So which one could represent the graph of the function that we have seen on the above slide? Let's check which one represents. Now look, the graph which is drawn here is a rational function whose vertical asymptote x equals to minus 4 and x equals to minus 1. We have 3 choices, A, B, and C. And also another information, y equals to 0 is a horizontal asymptote. For A, the horizontal asymptote is 0. For B, the horizontal asymptote is 0. For C, the horizontal asymptote is still 0. But for D, the vertical asymptotes are minus 1 and 1. It's not related with the graph. So still from the information, A, B, and C are possible. Now let's check the y-intercept. At x0, 1 over 4. That's not 1 over 4. At x0, it's 4 over 4, which is 1. Which is 1. So the function which is 4 over x plus 1 times x plus 4 is a possible rational function that can represent this rational function. So you have exercise, determine vertical asymptote, horizontal asymptotes, or oblique asymptote if it exists, and holds for this rational function f of x equals to x minus 1 over x minus 2 the whole square times x plus 1. There are answers. Here, if rational function has a horizontal asymptote, it will not have oblique, and vice versa. If it have oblique asymptote, it has no horizontal. So check the answers are given. Another example, the graph of a rational function is given here. Determine which rational function could represent the graph. So use necessary informations which corresponds with the graph, a vertical asymptote, a horizontal asymptote, x-intercept, and y-intercept. So after you write that, choose from this. Already the answer is given. Let's choose at D. So the lesson covers a rational function of the form f of x equals to p of x to q of x, where p of x and q of x are polynomials, and q of x is different from 0. So here in the lesson, we'll try to discover these lessons: asymptotes, vertical, horizontal, oblique asymptotes, whole occurs when a factor cancels from the denominator. This is all about the lesson. See you next time. Bye.